Think about the last time you were sitting in the passenger seat of a car. You're just cruising down a perfectly straight road, maybe adjusting the radio or something, and suddenly the driver just whips the steering wheel hard to the left. What happens to you? Instantly, you just lunge to the right. You feel your shoulder slam firmly against the door, almost like an invisible hand just reached right into the car and shoved you outward.
It's a completely universal experience, really. And honestly, it's incredibly comforting to our human brains to just feel that violent shove and, accept it as a physical push. Like, we like things to be intuitive. We want to believe something actually pushed us.
Right, but the truth of what's actually happening to your body in that split second is, well, it's so much stranger than just a simple push. So today we're taking a deep dive into two incredibly fascinating technical pieces of source material.
Yeah.
We've got the ghost in the engine, dynamics of spinning systems, and also the invisible lasso, engineering the laws of rotation.
Two really great texts.
Yeah, they're fantastic. And our mission today is to decode the hidden and, frankly, totally counterintuitive rules of our rotating universe. We are going straight into the math and the physics of how 19th century engineers had to solve these violent mysteries just to stop their new machines from, well, literally tearing themselves apart.
Right, and how modern designers still have to deal with the strict geometric tax, that's what the sources call it, that the universe places on speed.
I love how these sources take what could be just dense mechanics and turn it into this gripping story.
It really is a story, though. I mean, it's a hidden battle of forces. If we go back to your car example, that outward shove you feel against the door, it isn't a push at all. It's actually this grand dance between inertia and centripetal force.
Okay, let's unpack that a bit for everyone. So inertia is just the universe's natural stubbornness, right?
Pretty much, yeah.
Your body in that passenger seat was perfectly happy traveling in a straight line down the road. And when the car suddenly turned, it essentially just tried to leave you behind.
Exactly. And the only thing that kept you moving with the car was the physical structure of the passenger door pushing inward on your shoulder. That inward push is the centripetal force.
Okay.
Think of it like an invisible lasso. You have to tie that lasso to a moving object to physically yank it out of its straight line and, force it into a curve.
And engineering that lasso is where the real dilemma begins.
Yeah.
The sources break down the baseline equation for this force. It basically depends on the mass of the object, the radius of the circle it's making, and the speed of rotation. So how heavy it is, how wide the turn is, and how fast it's spinning.
But here's the really critical insight. The way those three variables interact is not equal at all. And that inequality dictates whether a machine works perfectly or, well, explodes into shrapnel.
I really want to visualize this. So imagine swinging a heavy bucket of water on a rope. If I make the rope twice as long, I definitely feel the pull on my arm increase. But if I keep the rope short and just try to spin the bucket twice as fast, my arm feels like it's going to completely snap off. So why does speed punish the system so much worse than size?
Because speed hits the system twice. So if you make the rope twice as long, but you swing it lazily, so it takes the exact same amount of time to make one full loop.
Right, it's just a wider path.
Exactly. It's gradual. You double the radius, you simply double the force. It scales really nicely.
But if I furiously whip the bucket around twice as fast,
then two completely different physical realities escalate at the exact same time. First, the bucket is traveling at a much higher physical velocity, meaning its desire to fly off in a straight line, its inertia is just far more violent.
Okay, that makes sense.
And second, because it is moving faster, it completes the loop in half the time. So that means you, the person holding the rope, you have to bend its path much more aggressively to keep it in that circle.
Ah, I see. So the bucket wants to escape more violently and I have less time to pull it back.
Yes, precisely. Because speed attacks the system from both of those angles simultaneously, the force doesn't just double, it quadruples. Speed is squared in the math.
Wow. Okay, so that squared velocity penalty, what the sources call the geometric tax, that creates a massive real-world dilemma.
It really does.
If an engineer wants to increase the power or intensity of a spinning machine, do they make it bigger or do they make it faster?
Centripetal force scales non-linearly. Doubling the radius safely doubles the load, but doubling the speed quadruples the stress. Always respect the geometric tax.
Let's look at the aerospace centrifuge mentioned in the sources. Imagine a massive steel arm in a lab testing some heavy electronic box.
That's a perfect baseline for understanding scaling forces, actually.
Let's lay out the starting point. The box weighs 2 kilograms. It's on a 3-meter steel arm, spinning at a baseline of 4 radians per second. Before we even do the math, what is a radian per second in plain English?
Oh, right. It's just a way to measure rotational speed. Instead of RPMs, engineers measure the angle the arm sweeps through, so a radian is just a chunk of a circle. 4 radians per second is a fast, steady spin, taking a little over a second to complete a full rotation.
Okay, so applying the mass times radius times speed squared, the baseline force pulling outward on that steel arm is 96 newtons. And again, let's translate that. What does 96 newtons actually feel like?
Well, think of 1 newton as roughly the downward weight of an apple resting in your hand.
An apple, okay.
Yeah, so 96 newtons is like having a heavy sack of 96 apples suddenly suspended from that steel arm. It's about 22 pounds of force.
Right. Now, say the engineers need to turn up the intensity of the test. They want to double the output. My instinct says just crank the motor. Making the arm twice as long means you have to rebuild the whole room, right? Spinning the existing arm twice as fast just seems so much easier.
It is easier, but it's a total trap. If they double the arm length to 6 meters, the force simply doubles from 96 to 192 newtons.
Yeah.
But if they take your route, keeping the arm at 3 meters and doubling the speed from 4 to 8 radians per second, remember, the speed squares. So the force leaps from 96 to 384 newtons, it quadruples.
Wow. So taking the easy route of just revving the motor puts immensely more stress on those steel hinges than just building a wider machine.
Vastly more, which is why building a bigger centrifuge is mathematically just much safer than speeding up a small one.
Well, it's one thing when we're talking about a metal box, but it gets genuinely terrifying when we talk about human beings.
Oh, absolutely.
Let's put the listener into a real scenario. Imagine you are on the Rotor. You know, that classic Fairground ride where you stand in a hollow cylinder, it spins up, and the floor drops out from under you.
Right, you're just glued to the padded wall. A classic triumph of centripetal force overcoming gravity.
So imagine a 50-kilogram teenager on this ride. The room is 2 meters wide, spinning at 3 radians per second. If you square that speed, multiply by the mass and radius, you get 900 newtons of force, pressing that kid into the wall. And the sources describe that as feeling like a solid, heavy blanket resting on your chest.
Which is thrilling, but completely survivable.
But say the park wants a next-generation ride that is 3 times wilder. So if they want to triple the thrill, why not just spin that exact same room 3 times faster? Take it from 3 radians per second to 9.
That is exactly how you end up with a catastrophe. Right. Yeah. If the park designers take the easy route and spin that same small room 3 times faster, we have to look at that squared penalty again. Speed hits twice. Tripling the speed scales the force by 3 squared. That is 9 times the baseline force.
Oh, wow. So the rider isn't hit with 2,700 newtons? Wait, they're hit with way more.
They're hit with 8,100 newtons of force.
Which is enough to literally crush human ribs. It would cave their chest.
Yeah, to keep the ride survivable while still tripling the intensity, the engineers have absolutely no choice but to build a massive sprawling cylinder that is 3 times wider across, a 6-meter radius. That scales the force gently and linearly to a survivable 2,700 newtons.
So size scales gently, but speed escalates violently.
Exactly.
You see this exact same bigger versus faster dilemma in modern drone design, too. The sources talk about how cutting-edge drones use micro-flywheels instead of chemical batteries.
Right, the kinetic energy storage.
Yeah, they're these perfectly balanced carbon fiber rings spinning in a vacuum. And the baseline here is a tiny 0.1 kilogram mass on a ring just half a meter wide, spinning at 10 radians per second. The structural force trying to rip the ring apart is only 5 newtons, just 5 apples of force.
But drone designers are always obsessed with storing more power.
Always. So they want to double the stored energy. Now, drones are obviously supposed to be compact. You can't just slap a giant 1-meter carbon wheel inside a tiny drone chassis. So the obvious choice is just to spin the tiny wheel twice as fast. Take it to 20 radians per second.
And once again, the math punishes the easy route. If they double the physical radius of the wheel, the structural force simply doubles to 10 newtons. But by doubling the speed, the force quadruples to 20 newtons.
And the text gives us a crucial limit here. The carbon fiber material they're using naturally snaps at a maximum structural load of 15 newtons.
Right. So choosing to double the speed doesn't just stress the drone, it causes an instantaneous catastrophic failure. The carbon fiber shatters, and the drone basically explodes into shrapnel mid-flight.
It paints such a clear picture of this geometric tax. But here's where we have to pivot a bit.
Okay.
Up to this point, we figured out how not to kill a teenager on a carnival ride or blow up a drone, as long as everything stays perfectly still within the spin. But what happens when things start moving across the spinning system? Like, what if that teenager on the ride tries to lift their arm?
That is exactly where we move from the predictable trap of speed into the realm of the truly erratic. To really understand this, we need to step back into the late 19th century.
Right, a world just completely obsessed with raw, rotating steel. We're talking about giant steam engines in factories, and the very first massive electrical dynamos being wired into cities by pioneers like Charles Steinmetz and all. When they built these faster machines, something really weird happened. The moment a switch was flipped or a valve moved, the engines would violently shudder. Massive transmission lines would spontaneously melt.
Yeah, the math they had for static systems, that standard Lasso math we just talked about, it failed them entirely.
The machines were acting haunted.
Because to catch this ghost, they had to realize something profound about geometry itself. When a system is spinning, changing your position or changing your speed doesn't just move you from point A to point B, it actually warps the physical geometry of the forces around you.
The universe essentially demands an algebraic correction.
Exactly. And to find that correction, they had to wake up the equation. Specifically, they needed the polar acceleration equation.
Oh boy, here comes the heavy math.
Just a little, the full math looks like this. Acceleration equals r double dot minus r times theta dot squared, all times the r hat vector plus...
Whoa, stop right there. You are completely losing me. What does any of that actually mean in plain English?
Fair enough. It means that when you're static on a wheel, you only deal with that one inward centripetal force. But the moment you move, dormant tangential terms in that massive equation suddenly wake up. New forces are born that act along the curve of the rotation itself.
Here's where it gets really interesting, because the sources introduce 2 brand new dynamic forces that emerge from that terrible math. These are the 2 ghosts the 19th century engineers were fighting.
Yes. So the first ghost is the Coriolis term.
Okay.
The math here is 2 times your radial speed times your rotational speed. This manifests as a literal sideways shove. It only exists if you are moving outward or inward while the system is spinning. And you'll notice the multiplier 2 sitting at the very front of that equation.
Yeah, I was going to ask about that. Why a 2? I feel like there's a physical reason for that.
There is, and you really have to visualize the space. If you're standing in the dead center of a spinning merry-go-round, you aren't really moving in a circle, you're just rotating in place. But the outer edge of that merry-go-round is flying by at high speed. So as you crawl from the center toward the edge, your circle gets bigger.
Right, I'm covering a wider path.
Exactly. To cover that wider path in the exact same amount of time, you physically must travel faster along the curve. Your linear momentum has to increase. But you don't have a motor to speed yourself up in that sideways direction.
Oh, I see.
So the spinning floor literally has to slam into your side to accelerate you up to match the speed of that wider edge. It hits you twice. Once because your distance from the center is changing, and once because your linear momentum must change to keep up.
That is wild. The universe is literally shoving you sideways to keep the math balanced.
Yeah.
And what is the second ghost?
The angular acceleration term. The math for this one is your radius times the acceleration of the spin itself. This is the massive yanking force that happens when the spin of the entire machine suddenly revs up or slows down.
Okay, to see these in action, let's look at the real-world historical machinery from the sources. Let's tackle the first ghost, the Coriolis shove. Picture an industrial power station in 1895. We have a colossal steel flywheel 20 feet across, spinning at a steady 2 radians per second. An 80-kilogram maintenance worker has to crawl out along one of the heavy steel spokes to grease a bearing near the outer edge.
And as long as that worker stands directly in the center hub, they are perfectly fine.
Right. But the moment they start crawling outward at 1.5 meters per second, they're slammed sideways by this invisible hand. They aren't pushed backward or pulled outward. They're shoved hard against the side of the metal spoke they're crawling on.
And we can calculate exactly how hard using that Coriolis equation we just talked about.
Right. So applying the mass, the outward speed, and the rotational speed, the math comes out to 480 newtons.
Which means roughly 110 pounds of invisible physical force suddenly slams into the worker just because they decided to crawl outward.
And unlike that brutal squared penalty of the carnival ride earlier, this Coriolis force actually scales linearly. So if the worker panics because they feel this weird shove and they try to scramble outward twice as fast moving at 3 meters per second, that sideways shove exactly doubles to 960 newtons. Over 200 pounds of force pushing them off the spoke. The faster you cross the lines of rotation, the harder the universe pushes back.
It's incredible. And once engineers understood this math, they stopped just fighting these forces and actually started harnessing them.
Right.
Which brings us to the runaway governor. It perfectly illustrates that second ghost.
The angular acceleration yank. So picture a massive steam engine. To control the speed, it uses a flyball governor. This is a spinning vertical shaft with 2 heavy 5-kilogram iron balls hanging on hinged arms. As the shaft spins, the balls naturally swing out to a 0.8-meter radius, and that physical lifting motion regulates the steam valve. It's a beautiful, self-regulating loop.
It's a great piece of engineering. But then, a catastrophic mechanical failure happens. Say, a valve gets stuck open. The shaft violently accelerates its spin at a rate of 6 radians per second squared.
And because the rotation itself is accelerating, those iron balls don't just lift smoothly anymore. A violent twisting force yanks horizontally on the metal hinges.
Right. Using the angular acceleration math, the mass, the radius, and that sudden spin acceleration, we get 24 newtons of twisting stress shearing against those hinges.
And if that runaway acceleration doubles to 12 radians per second squared, the shearing force doubles to 48 newtons. It's a perfectly clean, linear relationship.
And that predictability is crucial. Because it's linear, engineers know exactly how to design a failsafe. They calculate this exact angular force and install shear pins.
Oh, like bolts meant to break.
Exactly. Metal bolts specifically designed to snap at that exact threshold. By breaking on purpose, they disconnect the engine before the runway speed causes the whole factory to disintegrate. They quite literally use the math of the ghost to save the machine.
Which perfectly sets the stage for the climax of this 19th century mystery, the biggest ghost of all. Why were the first massive electrical generators physically destroying themselves?
Yes, Charles Steinmetz's AC generator. This was the absolute pinnacle of early electrical engineering.
You really have to completely shrink our perspective down for this one. Imagine we are inside the copper windings of his massive generator. The source text models a concentrated packet of electrical charge. It has a tiny effective mass of just 0.02 kilograms. It's spinning on a rotor at a half-meter radius at a blistering 50 radians per second.
Under normal operating conditions, that current flows smoothly outward into the city grid, but then a massive short circuit occurs down the line.
Right, the electrical load just vanishes. The magnetic flux lines inside the generator violently snap inward toward the center axle at an astonishing speed of negative 30 meters per second.
The negative sign in the math just indicating that the movement is radially inward toward the center rather than outward.
Right. So imagine you are an electrical engineer in the 1890s. What happens when a nearly weightless electrical packet collapses radially across a massive spinning magnetic field?
We use the exact same Coriolis equation that shoved the maintenance worker against the steel spoke, because we have a radial speed and a rotational speed.
Wait, really? Even for electricity?
Yes. The geometry applies to anything with mass in motion. So the math gives us an instantaneous transient cross force of 60 newtons.
Let me stop you right there. For a nearly weightless packet of electricity, A localized mechanical force of 60 newtons, which is about 13 pounds of force slanting sideways into a thin copper wire, is an absolute hammer blow.
It's completely devastating, and if that short circuit is even more violent, say the magnetic field collapse speed doubles to 60 meters per second inward.
Then the shock wave doubles to 120 newtons. This mechanical force, generated purely by a mathematical quirk of geometry during electrical collapse, explains exactly why these early dynamos would literally rip their own heavy copper windings right out of their metal slots.
They were just being hammered to death from the inside by a ghost force.
It just absolutely blows my mind that a brutal physical shock wave can be generated by an electrical short circuit simply because the geometry of the system happens to be spinning.
It connects everything. What looks like an erratic, unpredictable ghost to an untrained observer is actually the rigorous, beautiful poetry of coordinate geometry. By tracking these mathematical terms, those 19th century engineers mapped the shifting frame of reality.
So what does this all mean for us? From the squared velocity tax on modern amusement park rides that dictates whether your ribs survive the spin, to the linear sideways shove that nearly knocked a maintenance worker off a steam engine spoke, to the mechanical destruction of an electrical generator. Well, the laws of the moving frame are absolute.
They are totally inescapable. They scale with every single step you take across any turning world.
It really makes you realize that every single time you turn a corner too fast in your car and your shoulder hits that seatbelt, you aren't just feeling a bump in the road. You are physically feeling math happening in real time. You are feeling velocity being multiplied by itself right against your chest.
That's a great way to put it. And if we really want to push that perspective, think about the fact that you, right now, as you listen to this, are standing on a giant spinning system called Earth. We just saw how a worker merely crawling outward on a 20-foot flywheel creates a massive 110-pound sideways shove.
Right, the Coriolis force.
Exactly. So imagine the unfathomable scale of the invisible Coriolis friction that massive weather systems like hurricanes or rockets trying to fly outward into space have to fight against every single day just to move across our spinning planet.
That's incredible.
The Earth itself is the ultimate flywheel, and that ghost is always pushing back.
That is an incredible visual to leave on. The ghost in the engine is everywhere, dictating the shape of the clouds above us and the rockets leaving our atmosphere. Thank you so much for taking this plunge with us today. And hey, next time you're in the passenger seat and the car whips around a turn, just remember that invisible hand shoving you into the door. That's just the universe balancing the equation.